Everybody join. Hello.
Yes, sir. Good morning, sir.
Good morning, everyone. Only eight are there. So, shall we continue that evenings every day? Do you think our usual times will get back? Because see, if we do that only 1 hour just like that is passing. Some are coming late, and you will have classes of next hour.
Okay, sir. I have to ask with everyone. If everyone agree with this, then we can do, sir.
Otherwise, you see, okay, today you have another class after this. 12 at 12. Do you have class?
No, sir. You can extend, sir.
Okay, so fine. Today we'll do little bit because you see these calculations the way we write on the online, no. So it's taking a little bit time. So that's why we want to at least little extra time it may takes. But if we take usual hours like 11 and 12, 11 and 10 o'clock, but we are losing time. So that's what is my concern. So anyway, so I'll just try to see what we have done last class. So we derived this Bernoulli equation. So Bernoulli equation basically, we suppose you want to have a free surface, right? So free surface condition we derived some time back. So this is the free surface condition where eta is unknown here, right? So to get that unknown back, you need another equation. So that another equation, this is one boundary condition. So to get that one, we'll basically use this integration, the momentum equation at the surface. At surface directly you take it. So if you integrate is also you'll get the same thing. So integration. So how did we do this? You take the momentum equation and you just do replace it, and finally momentum equation takes this form. Okay. So this form now you try to put now if you are working with water waves, water. If you are working with water fluid, then you can consider it as you assume that is also irrotational motion of that fluid. The flow is irrotational. In that case, del cross u equal to 0. Then you will have a velocity potential phi. This as you see what you are seeing right now, right? You have already seen. I just sent some pictures from vector calculus book. Okay, so that is the proof that the if you actually see the WhatsApp, the first page is about the potential field. That last theorem, no, 24.12. The theorem says for a field of vector A to be potential field. So that means there exists a phi such that gradient of phi equal to A. Okay. So if and only if it is the curl of, so instead of U, you have A here. So this is the theorem. So that theorem, if you actually look at the other the proof that I sent from that book, you might see some some in a different way. So try to understand neatly, and the main idea, and neatly you write so that you put it like U and phi setup only, not A, and don't simply copy and do it. So you understand and write in your own way. So what exactly the idea, and how you get that, how do you construct that phi? Okay, so whatever that is the proof. So necessary and sufficient condition. So if and only if, that is what is done. So there exists a unique means basically necessary and sufficient condition. Fine. Of course, it won't be unique here also. I mean unique means up to the constant. Okay. So if I multiply simply phi plus some constant, obviously you'll have here also, right? So I'm only saying that the actually unique you should remove it. But okay. So unique in the sense you can absorb something, whatever constant you can absorb into that as a potential. Okay. So it is not actually unique. So it's your potential function. Okay. So that is uh, if you add phi plus some constant, gradient of that constant is 0, right? So in that sense, it is not unique. So don't, maybe better you remove unique. What we should say is del cross u equal to 0 implies there exists implies grad phi equal to u. Grad phi equal to u implies del cross del phi is anyway 0. Okay, that is immediate. That is what is the meaning of sufficient, necessary, and sufficient condition. So unique, I think the unique is the correct, not correct thing. So you can remove it. Okay. So maybe I'll correct it and let you know. So this That unique, whatever you have written, that unique, you can remove it. Okay. So this is one of the assignment that I've sent you on WhatsApp. For those last two, I think list will be 10 and 11. Okay. So who are all those people? I try to pronounce their names so that they take. So Pragna and Kush Kataria. Okay, these are the two
Yes,
people. Yeah, just go through this proof and try to write neatly so that you everybody should understand. That is one. And I also sent. Did I send? Yeah, there is another one for that Helmholtz theorem. See, you can easily see. You try to go through and easily see that you can actually construct that one. So the last file that I sent. Oh, I send. I think I didn't send. No, that one. That Helmholtz
so
theorem.
you
Yeah.
sent one PDF of almost.
Yeah, that PDF is basically Helmholtz theorem. So what you have to understand is, if you see, uh, basically the Dirac delta function, have you done in your courses? Anytime did you see the Dirac function? Dirac delta. Dirac delta thing, if you apply, and you have a vector function fr. Okay. So if you look at that theorem, you try to understand finally that fr, I am able to write like del dot c. See, at the end I will show you. So exactly, if you open that file and you end up seeing the fr is your potential vector that is your vector function. Basically, r you remove it. Fr is a vector. That vector is actually minus that vector thing is gradient of v plus curl of a. Okay, so some a and phi exists here. Okay, as you see. So what is actually required for us is only that phi is not required anyway. So you add any phi, grad phi, scalar function is actually true. Okay, then del dot del phi, right? Delta. What is that we have seen in the last class? Okay, so this irrotational motion, first we have derived that Bernoulli equation. That you leave it. Another assignment is del dot u equal to 0. There exists a velocity field such that u is actually given as gradient and that curl of v. Okay, so if you actually see here 10th equation in your Helmholtz theorem PDF, that a of r is your v. Okay, del cross v equal to f. F is your u there. Okay, and what is that remaining is also you can have that grad phi also, some grad fees also you can derive. Okay, so once you have this, so that is the rotational component, and the rotational component is del cross a, the irrotational component is del phi. So finally you see that del dot fr is 0. What is the reason? Del dot fl. So if you look at that, fl is this one. Del dot fl somehow del dot. So the divergence of gradient is, I think, is 0. Okay. So that is irrotational thing is like you will have only u equal to, yeah, I think I wrote wrongly yesterday. What you should, this irrotational part is basically some phi you will get it. So this you should write it like, if I see it here, that equation number 10 in your Helmholtz, that PDF, you should write like some gradient of phi. Okay, some gradient of phi. You can always, this is your basically Helmholtz theorem. Okay, the Helmholtz theorem tells you that I can decompose into rotational curl of some vector field plus gradient of some scalar field. So this is different. This Helmholtz theorem is what you have. This you can always do, right? Now you look at that incompressible flow that you have. So del dot u equal to 0 is given. Okay, this one implies there exists a vector field v. So I'm ignoring that gradient of phi here, such that u equal to del cross v. Now if you look at this curl of gradient is always 0, no? So any v, if you add some gradient of phi of scalar function, now if you add it del cross, if you take the del cross u, I mean del dot u, right? That is your del. Yeah, u is equal to del cross v. Yeah, this first part will give you what you want, right? That is unique, right? So when you add this any quantity to V, I think that is the existence of that V is coming from your Helmholtz theorem. First part, del cross U, right? Del cross V in your Helmholtz theorem is actually acting as your V in your that whatever you have written, that there exists a vector field V. Okay. So if you really don't want this, let me put it like this V, that V different. So let me put it here as some A. A is a vector field. So A is your V. Okay. You understand now? Okay. So you can
Yes,
always
sir.
see that, yeah, you see that del dot F, del dot, you see, Helmholtz theorem tells you that why we say that this is a irrotational thing, irrotational, because this component, when you take the dot product with this, it is always zero. Such a phi exists. Okay. Not any phi you are adding. So basically, you are not adding this. So this is a unique way. This is the whatever Helmholtz theorem is basically. Any you are uniquely writing as rotational component and irrotational component. But what you require in that in this bracket, this star, whatever star, if I put it, if you have irrotational flow, that velocity vector is uh, gradient of, I mean, the curl of V. V is actually your A. So this is only A. So it is not unique. Okay, because there is another component is also there, no? So that when you take the divergence, it will be zero. So I will say here such that, so in the whatever is Helmholtz theorem, such that del dot del phi is zero. Okay. So this is what is Helmholtz theorem. So this is actually, if you look at that equation, after that equation 13 in that file, del dot FL. FL is your first part. So that is your FL is 11. Equation number 11. FL is your gradient of P. So that part is anyway zero. So such a decomposition is always possible. That is Helmholtz decomposition. That is the Helmholtz theorem. Okay. So now that I have given you the material, so you do it, try to understand. If you have issues, let me know. So you should understand every point and you make a note and finally submit the assignment so that everybody should understand. Okay. So this is the assignment for both of you. These two are the assignments. Okay. So the last class, what we have done is the Helmholtz, the momentum equation that we have. So you see here, this is your momentum equation. We modified. We have not done anything. We put it in a different form. And in a particular case of irrotational motion of homogeneous fluid, because rho equal to rho of E only. Okay. That is what once you integrate, that you try to integrate, gradient of that equal to zero. So whatever the remaining gradient of something, that something is become constant, that equation is called after integration. That's kind of integration. Derivative equal to zero, you will integrate. So that function you get it as constant. That is actually for irrotational homogeneous fluid. That constant is there, same constant. Okay, that is why because the gradient is zero, derivative is zero. So this is called Bernoulli's equation. This is one case. Now we will take this momentum equation. Now I am saving this and opening a new file. Okay. So what I do is I'll try to write it. I look at this other today's lecture. And then date is this. So you take this dou u by dou t. Okay, this is the momentum equation basically. I'm continuing from there. Okay, dou u by dou t plus grad of half norm u square, right? Square minus what else you have? This is 1 minus u star, I mean u cross del cross u plus 1 by rho grad p. P is the pressure function, okay, of the position and time. And rho is Rho is basically the density. So plus external force, so we write it as gradient of Gz. Okay, G into Z. This coming from gravity, gravitational force. This is equal to 0. This is your momentum equation. Okay, so momentum equation in another form. Okay, so once you have this one, now what we do now? Now we will remove the restriction that it is a homogeneous fluid and also irrotational motion. Let's not do this. Okay, so is del cross U is not equal to 0. So let us do that one. What do you do now? So to now what we can do, del cross U. Now this is for in general case. I am not doing anything. I am just doing modifications only here. So do U by dou T plus gradient of half. Whatever restriction comes, we will see. Okay, that time I will write it. So this one minus this we write it as U cross omega. Okay, that is your vorticity vector. This is your vorticity vector. That is your vorticity now. We have defined already. Plus 1 by rho grad P plus gradient of Gz. Grad Gz equal to 0. Up to here, nothing else. So I just replaced del cross equal to that vorticity vector. Now I'm trying to do something here. See, in general, let's see what we are doing right now is simple mathematics. Okay, so that this quantity I'm going to write in a different way. Okay, so this I want to modify first because rho is, you see, rho, if rho is a function of P, I can now put it as a gradient of something inside. Okay, this we can write it like 1 by rho grad P. I can if suppose rho is constant, I can take it inside, right? Grad P by rho I can put it. Suppose rho is function of T, still I can take it inside, like you did now homogeneous fluid earlier. Now even if it is a function of P, I can take this rho is a rho of P, then I can take it inside. Okay, so but take it inside, but I will put it like gradient of some function of P. Okay, that is what we will put it. So that is where some integral will come. Not only so, that such fluids are where density is depending on rho P. Okay, rho density, rho depending on only on the pressure. Such fluids are called barotropic fluids. Okay, so that is what we can easily show that you can do that one. But in general, mathematically, if we do, I think any rho, rho is the density. Any rho need not be function of P. Let us see. Okay, so whatever we do this calculations, I think it's valid. Or maybe if you just see this is a digression. Whatever we are doing is simple mathematics. Let us see. Since what we do is df. F is any scalar function. Okay, we don't write since. Let start with this. Let f be a scalar function. F be f of x, y, z. T also you take it, doesn't matter. Okay, be any scalar function. So then what happens? You know the df, right? Total derivative. So total derivative is okay. So now I don't want that t variable. So I will consider it as a function of x, y, z only. Okay. So let's remove this one. Okay, though actually in your rho it is actually rho, rho function. If you actually see, rho is actually depending on x, y, z and t, but we are interested only first three variables. Okay, first three variables you can write df, total derivative. So that's what we do for rho. So don't worry now. So f be any scalar function of x, y, z. Then what is df? Df is dou f by dou x into dx plus dou f by dou y into dy plus dou f by dou z into dz. Okay, so this, if you might have seen no earlier. So dx, dy, dz is like dr. Okay, position vector. D of position vector is represent like this. This is the dot product with whatever is left. What is left there? Grad phi, right? Isn't it? That is simply grad f, right? That is grad f. This we can put it like this way. So grad f. Okay. This is what we do. So now what I try to do is I take some dx dy dz, that is dr dot product with. Now I put it like 1 by rho grad p. So this I will write it like 1 by rho is nothing to do, no? So grad, this is grad p. Okay. So this is equal to 1 by rho is anyway scalar function that I can take it out. So we'll have 1 by rho into dr dot grad p, right? The grad you put it and you, so that this is your p function p here. Now what is this one? Now from you look at, observe this one. This means df, right? Dr dot grad acting on f is actually df. So dr dot grad acting means this is actually our dp, right? Isn't it? This is nothing but your dp divided by rho. So total derivative of p divided by rho. The total derivative is only xyz variables. Okay. 1 by rho as it is. So this quantity is simply dp from this. Okay. So this is equal to, now how do I write this one? This I'm going to write it like, I'm going to put it like a derivative, total derivative, and I put it like integral. Integral derivative will go, right? Yes or no? Integral of f dx is simply d if you put it. So what is this value? What is this value? F only, right?
Yes, sir.
F is function of x. What is d? Single variable, it is simply d dx. That's what it means. D means. D means basically that d is like d dx. Okay. So d dx, if you put it finally fx, you remove it, it's d dx goes, so finally, so basically this way you look at it. There is like a total derivative point of view if you look at it. Okay. So it becomes f. You try to understand from calculus. Okay. If you have problems, we will restrict ourselves with only with the rho is a function of p. So this d integral, if you put it together inside f, I'll write as it is here. So whatever here, so that is your dp by rho. Okay. So what is d of this quantity? D of this quantity is like dr dot grad dot del operator acting on this p, whatever here. What is that you have here? So inside that is integral dp by rho. Do you understand? Instead of f, you have this one because this is a d of f. F is this one. Okay, this is what we have. Now, can you see this now? So whatever you have here is, this is nothing but dr dot product with grad of this integral dp by rho. Okay, so left hand side is dr dot, so dr is arbitrary, so this implies 1 by rho grad p equal to grad of this integral. This is your dp by rho. This is true for any rho is a function of x, y, z and t. Need not be functional, because can you, or is there anything that we can do this? You can deny. Can you deny? So I'm just saying that this is true. This is true for every row, for every row, right? I don't have any restriction right now. Like you have rho should be function of t, rho should be only function of function of only p. I don't have any such restriction, right? Okay, if rho is a function of p, we can do that. Whatever you are doing, I can justify in a different way. Okay, I'll show you that also. Now I'm saying if I do like this, Is there anything uh, you can go against? Hello? Can you say, do you have problem if I write like this? Is there anything wrong here? I'm not putting any restriction on P, right? I think it should be when you write like this, the integral of what? dp. That means rho should be function of P only, right? Isn't it? You are doing dp integral, total derivative of integral dp by rho. So P is also dp divided by rho. Rho should be function of P, right?
Yes, sir.
Yes, sir.
Sir,
Whatever you underline here, that means the rho should be function of P only, not any function of x, y, z, right? That's why some other textbooks, you may see that the rho should be only rho of P. We will confirm that, okay? So rho is rho of P. That at least this is fine, right? If rho is simply a function of x, y, z, and t, and what is the meaning of integration of this function with respect to dp? No, it doesn't make sense, right? So this is the meaning. I think this is okay. So is equivalently we have done. So there is nothing. I think we have not done anything extra. Okay. This is one way of doing this one. Okay. So this, if you like this way, you do it. Otherwise, also we can do. Okay. So what we are trying to do is we want to put this as a dp by rho as a total derivative of something. Okay. So how do we put that as total derivative of
sir,
something? Yeah.
sir, as you defined earlier, like total d integral f, like f a function of x and then dx, sir, is equal to f. So, sir, how can we directly take dp by rho equal to, so like then f would come out, no, outside of integral. If rho is a function of p, sir, then it should like outside the integral only 1 by rho should come. No dp should be there.
If rho is function of x, y, z.
Uh, yes, sir. But here you said no, that rho is function of p, as we are taking with like integration with in terms of p only, sir.
Yeah, that's what. See, this looks like dp by rho is that's like, you are integrating, right? The integral with respect to what? See, we wrote d and integral is like some loose way we have written. D is the total. It's like a d is the derivative. Integral is integral. So it's like they are getting cancelled, right? But still, exactly which variable we are doing, we are not sure. D and integration, right? So dp by d. So if you say integral, if you are putting first, then you are writing integrals like you are integrating dp by rho. So rho is a function of p, means this integral makes sense. Now if I take the derivative, the total derivative of this, whatever may be function of p, okay, it's like here. It's like fx dx, okay. So what is your fx? Fx is like 1 by rho of p, 1 by rho of p into dp integral. This is a total derivative. What is this total derivative? This is a total derivative of something equal to, because of the integral. So this integral is nothing but f. Why is this one? What is the total derivative of this? Once you differentiate this one, means what? This is something like, you're fixing some point x naught to some x. Okay. That is what it means. So what is the derivative? What is the meaning of derivative? So let's put like d dx. So d means what? Total derivative, right? So let's put d dx. Okay. So d dx. Here it should be d dp, that means. So if you put d dx, it is actually fx, right? That is what it means, right? So what is the d means? D operator means what? That is like here df. Df means total derivative. In many variables, we know this is the total derivative. In the single variable case, d of this derivative of with respect to x only. This is simply differentiates the Leibniz rule. This is simply fx. Yeah, it should be like this. So this means for you it should be ddx, right? So it should be ddp. This should be ddp. If ddp, I don't have issue. isn't it? DDP of this is okay, but what is the meaning of loosely writing D simply D and integral? Okay, that you need small justification, but still, if it is DDP, we can do this. DDP, that means, okay, how do I put this? If you have many variables, there is no issue. So the thing is, you have many variables there. So that's the reason P is a function of XYZ. DP is also function of XYZ. See, overall, you don't worry about this one variable case may be confusing for you, so that you are writing DDX. So here you have multivariables. P is a function of, after all, DP. Leave it, forget about D. What is DP? DP is, after all, dou P by dou X into dx plus dou P by dou Y into dy plus dou P by dou Z into dz plus dou P by dou X, because P is a function of X, Y, Z. Overall, it is function of X, Y, Z and T. Rho is also function of X, Y, Z and T. So in that sense, if I write D as a total derivative of all the variables, X, Y, Z and T, if you put it, then I will have the integral of that. Okay, so this some loose sense. Okay, we will try to see this one. Okay, I'm not sure. So this is the total derivative of this integral of what? Integral dp by rho. Now it is a function of x, y, z. What is the meaning of integral of either it's integral dx or dy with respect to what? Okay, it's not
Yes,
clear.
sir. Thank.
But if you say
So
t and
suppose,
integral lose, yeah,
so
yes,
like, if we take in terms of x, y, z separately and then do it the total differentiation, so then we can write. But if only with terms of p, then it won't be as such you have written, right?
yeah, maybe there is some, you need some work to do this one. So can you just try to see that this is actually equal to this? Then we can remove this restriction, whatever we say here. Okay. Otherwise,
Okay, sir.
for rho equal to rho p also, still I have issues. This way, this is looking like a little mathematical, but you have to justify exactly. So if you write like this, for example, what is the d integral? D integral means what? Dou x of, let us write this integral. Okay, this integral into dx. So dou x dx. I'm not sure what is the meaning of this one. So this is something like, crudely we wrote like here df, right? This df we are just replacing. So this is dp by rho, right? So we are writing right now. The only justification is d and integration. This is the d is the derivative. Integral is total. D is the total derivative. No, after all, it's derivative. So it's like, but little justification mathematically required, d and integration. So that will go the same as dp by rho. Okay. So you don't. So this needs some mathematical justification, really. I mean, whatever you learned. So. But this we will come to that again. So if you do like this, it looks like, if I do something like d and integration, then I can remove this restriction. So we are still questioning. Okay, this way we can write. This is still question. Okay, we'll put it like this, and then okay, now at least I'm just leaving it to you. I'm not sure. Okay, we will try to justify again. We will come back to this. So right now, what you do is, if this is the general way of doing. Okay. So if you don't do this, let me put it as like, if I want rho to be, now look at the case. As a case, let rho be only rho of P. Okay. Then what you really want is dP by rho, right? You want dP by rho equal to what? Derivative of something, right? It's an exact differential. You want it to be exact differential, right? So perfect differential means what? You want this to be some d into perfect means some, let us say some q, for some q. Okay. So if you do this one, What is that you get here? Rho is rho of P. Okay, rho is rho of P. So dP by rho of P equal to, let us say, d of some perfect function. So let us say this is some q for some q function. Okay. We will write it like dot if, let us put this here. If this is okay, this is integrable. dP by rho is integrable. So that means a derivative of something we are writing. Perfect integral. How do you see this one? This is equal to, how do you write this? So we will write it. So if this is, then what we have is dP by rho. Let me put it like dP by d rho into 1 by rho is there, right? 1 by rho is there already here. So dP by rho into dP by d rho. I just divided it. Okay, equal to dq by d rho, isn't it? So
Sir, here
yeah.
Q is heat energy.
No. Some function I'm just saying. So I'm
Oh, okay, sir.
some,
Okay.
just like mathematics, you don't know. If it is the total differential, this is dP by rho. I'm writing like total differentiable for some function. For some function q. I'm calling it q. Okay. Then how do you integrate this one? So this will be you understand now? Can you take up this challenge? At least this one, whatever we are doing, d into integral. Okay. So you try to understand that one. So we will come to that one anyway. So but here we'll justify. Okay. Simple way, this way. So we want finally dP by rho. See, what is that we have done? dP by rho, we want to write like total derivative of something. So that integral dP by rho, that we are calling as q. Okay.
Okay, sir.
So that integral dP by rho is basically your q. So that is what we want to show. Okay. So you have this differential equation now. So if this is this, what should be your q? So what should be your q? Yeah, that's all right. So from this, I can calculate, I can integrate both sides, right? So you integrate dq by d rho into d rho. With respect to d rho, I'm doing. So that the right hand side I did, the left hand side also you should do that. 1 by rho dp by d rho into d rho, right? D rho cancels. So what you have is integral dp by rho, right? This, if you remove it, that's what you have. What is left hand side? Left hand side is, what is left hand side?
Only Q, sir.
So q is actually integral dp by rho. That's all right. This is simply differential equation. You see it like dq by d rho equal to, so this you put it on the right hand side. Then that is an equation, right? Isn't it? You differentiate it because p is dp by rho. Rho is rho is a function of p. So p is a function of rho also, you can think, right? If rho is a function of p, p is actually, you can write it as a p is a function of rho. Okay, so you think that is actually depending on each other. So you just see this dp, I divide with d rho. So it's like a differential equation, dq by d rho equal to something. This is like right hand, left hand side is like a known function. Okay, P, and you simply integrate both sides. You are getting this one. Q is also true, right? dq equal to, what is the dq? So immediately you have dq, no, dp by rho, isn't
Yes,
it?
sir.
So that is what exactly. So here dq, so this whatever you write here, it makes sense. Okay, so for every rho equal to rho of p, rho equal to rho of p, I think it makes sense. Just now, that's what we proved. Any question up to here? Have you followed? About that one. So that is simply D means simply one derivative. If rho is rho of P, you don't know what is that integration or all. So you simply write you like this. dP by rho equal to dq. So Q is actually your, this is your Q. Q is actually we calculated. If that Q itself is this, then the other way also we have that dq is nothing but dP by rho. We have done, right, both ways. That means this is true. I think is only valid only like this. Okay. So rho be rho. So if rho is not a function of p, rho is function of x, y, z, and t, and you integrate dp by rho, it doesn't make sense, right? So whatever you're doing is only for rho is equal to rho of p only. So now we come to the physics. So if rho equal to rho of p, then such a fluid is called such a flow. Okay, a flow. Then a flow with let's write like this: a flow with rho equal to, so definition, a flow with, a flow means you have a fluid with a velocity, elastic field was where the density is function of p only. Is called a barotropic flow. Such a fluid is called barotropic fluid. Okay. If the density is depending only on the pressure, that is barotropic fluid. A fluid with density is only of pressure. Barotropic fluid. Barotropic means basically pressure. Okay, it depends only on the pressure. So the fluid density depends only on the pressure. So that tells you that story. Okay, barometer. No, physics you might have seen in school. Baro something. No, so the gauge the pressure, right? So that's how you get this flows. Flows means such a fluid flow in that such fluids are called barotropic flow. Okay, do you understand?
Yes. Is
what
there
I
any,
if at
so
all
is
I
there any,
if at all I used to, what I thought is because mathematically I'm only trying to think like a mathematics, mathematically. If you look at it here, a d of integral I wrote as rho of p. As rho of p. Okay, rho of p. If I don't take, I can think of rho as rho of x, y, z, and t. Okay, this differentiating, that is simply dp by rho. That is your left hand side. That makes sense. That is what we have actually shown. Okay, this is the proof of let us say star. We'll put it not, we don't write it as case. For example, this one you make it a star. Okay, so proof of star, I'll put it here so that you will understand. You will not have any confusion. Fine. This is your star. This is what we have shown. Okay, so that's shown. So now this we can see like this. That implies this one. This is true where provided this is very important. Rho is rho of t only. Okay, I think see some mathematics textbooks it is written like the d into integral. So you think that rho is basically any function is it's fine. Actually, it is not. Okay, you have to think closely. So the integral dp by rho. So integral dp by rho, p is a function of x, y, z. That is anyway dp. You are considering p. But what is rho? If it is rho is only function of x, y, z, and t, it should be function of p only. You can integrate. Otherwise, it doesn't make sense. So whatever you are doing is only for rho equal to rho of p. That is another technique. Rho, you can get as a perfect integral. There is no exact equation. So dp by rho of p is nothing but some exact equation. Exact equation means what? I can write it like a derivative of something. Okay, just like x by y. What is the total derivative? Equal to, what is this one? This is like y square y dx minus x dy. Okay, this is perfect. This is exact equation because this is the derivative of some function. Similar way you are doing. Okay, so that dq.
okay, sir.
This is the proof that we have given. So I think it's all right. Okay, so this is what we have done. Now you go and put it into your momentum equation. Now come back to the momentum equation. So this I am going to replace now. So that integral that you have right now, dou u by dou t. So that implies the momentum equation becomes dou u by dou t, dou u by dou t. This u as omega, I take it to the other side. Okay, so this gradient of this half norm u, this Euclid norm square, this plus 1 by rho grad p. Now I'm replacing with, what should I put? 1 by rho grad p gradient of that integral dp by rho.
Yes, sir.
This is only function of p, not for any other thing. So this only for barotropic flows only it is true. Now I'm writing. So this one, and what is the other one that you have? So this plus gradient of this gradient of gz. Okay, gz. This is your external force, gravitational force, equal to, now I take it to the right hand side. So that u cross omega, I take it to the right hand side. So this is your vector cross omega. This is another vector. So this is what is your momentum equation now. Okay. So I have not done anything. This is the momentum equation for barotropic flows. Okay, barotropic fluid. Okay,
Okay, sir.
now I will define. See, usually how it is done, I'll just show you. So you will say something called. I'm just this is just a notation. Okay. So usually textbooks they say we have derived, we integrated this equation for irrotational flow in order to for consistency. Similar way we'll try to do. We're just doing so this implies. Let me write. You will understand what it is. Dou u by dou t plus whatever. See, I cannot integrate now. Suppose if you write it as gradient of some scalar potential, then we can integrate. Then everything in the delta. Okay, so then omega equal to this, omega equal to 0 in that case, because that is irrotational. So I can integrate. So that whatever integration you are doing, that is you are calling it Bernoulli equation, because it is coming as an equation. Now we are not integrating. So, but certain part of it we can write it like gradient of something. So we'll put it like gradient of whatever is inside here. So that is half this u bar whole square plus integral dp by rho. Rho is a function of p. Okay, and then plus gz. This quantity I put it as a gradient of something equal to u cross omega. Then whatever this quantity, if you define as if b is a function, we call it some b is a vector. Is it a vector there? It's a scalar function, right? It is just a scalar, it's not vector. So
Yes,
let's
sir.
call capital B of x, y, z, and t. Okay, right? This is like b when you write it, x, y, z, t, or simply b of x, t. Okay, so this is, if you define it as half u bar square plus integral dp by rho plus gz. Then so what you get is this d dou u bar by dou t plus grad b equal to u cross w, u cross omega. Okay, this is now your momentum equation. So momentum equation is this now, right now. So where b is called, or you simply say b is called Bernoulli function, known as Bernoulli function. Bernoulli function. Okay. Once you integrate, you call this uh, Bernoulli equation. So when can you integrate now? So what else you can do? See, this is like you can't do anything, no? Dou t. Now you can't replace u by gradient of v to integrate. That we have already done in that case. So in this case, what happens is, if you look at this, what is u bar? U bar is your uh, velocity vector, right? That is your velocity
Yes, sir.
component, UVW.
Yes.
So that is tangent to your basically your streamlines, right? So u bar is actually is tangent to streamlines. What is omega bar? The same way we define, but you don't know, you can't imagine your omega bar. Omega bar is a vector, is tangent to verticity lines, right? Verticity lines or vertex lines. We say verticity line. We call this verticity lines. Okay, it is tangent to verticity. This vector is tangent to verticity lines. You don't know, you can't imagine right now. If the flow is like this, that is those tangents are your basically u. This we know, you can imagine this is your streamlines. Okay. Similarly, vertex lines means, So what actually you are doing in the fluid? Just look at this. This is like, let us say going like this. Everywhere, let us say flow is like this. So imagine this point. This point